Welcome back. Let's talk about differential equations in general. Differential equations can be categorized in different ways. A very important distinction needs to be made between linear and nonlinear differential equations. In practice, the world is nonlinear. In other words, all systems are nonlinear. However, the control techniques that are most established assume linear differential equations. While nonlinear control techniques are also undergoing significant research, oftentimes it is much easier to take a nonlinear system, linearize it, apply linear control techniques to it, and it works sufficiently well. Furthermore, it is much easier to solve linear differential equations analytically. In fact, most nonlinear differential equations cannot even be solved analytically. You have to solve them numerically, and we will cover that part too. But linear differential equations can be solved both analytically and numerically. There are only a very few nonlinear differential equations that can be solved analytically. Now, when you can obtain analytical solutions, that would be ideal because they are precise. Numerical solutions are approximations, but oftentimes they are your only option. In fact, when analytical solutions are available, you can use them to check numerical solutions and vice versa. And so, how do we know which differential equation is linear and which one is nonlinear? Let's consider this simple 1 degree of freedom system with a mass, a spring, and a damper. Let's also assume that there are two external forces, F1 and F2, which are applied to the mass. They can change with time. They do not have to be constant. Let's model it mathematically. Since it's a 1 degree of freedom system, the mass can only move horizontally. It cannot move vertically, and it cannot rotate. So we only have one equation of motion here. These are my external forces. This is my spring force. I assume that at this time instant, the spring is stretched, so the force needs to point to the left. And this is the damper force. I assume that the velocity of the mass is to the right, therefore the damper force needs to be to the left. And all that equals mass times acceleration. If I rearrange it, I will have this form. Here, F1 and F2 are external input forces. They can be your control inputs that enter your plant, or simply disturbances. Both of them enter the plant. Solving a differential equation analytically means that you obtain a function for your differentiated variable, in this case x, because here x is differentiated with time, and that function will only have time as an independent variable. You will not have any derivatives there. For example, a solution could be x as a function of time equals all this. You only have time here, and this is what comes out of the plant. You describe your system in the plant using differential equations, and then you solve it either analytically or numerically, and your solution to the differential equations comes out of the plant. And then that solution goes into the controller, and the controller's job is to generate the right kind of external input forces so that your system would behave as you desire, so that you would have your desired solution. For example, it might be countering the disturbance force. A disturbance force is something that you cannot control. It simply appears and you have to deal with it. And now, this is very, very important. This is the key. You really need to pay attention now. Now you will know the difference between linear and nonlinear ordinary differential equations. I will take this case and I will separate it into two cases where I apply each input force to the ODE individually. If the solution for this case is this one, and the solution for this case is this one, where A and B are some constants, then the ODE is linear if the solution for this case, where I first add up the input forces and then apply it to the ODE, is this one here. In other words, this is this case here. I'm applying two separate input forces to my system individually. I get the individual solutions, which are these ones here. So this one, it would be this one, and this one, it would be this one, and then I add them up, and then this case here, it would be this case where I first add up the input forces, and then I apply their sum to the ODE, and then I get some solution. And so if these two cases are equivalent to each other, meaning that both of them will produce the exact same solution, if that's the case, then you are dealing with a linear ODE. This is called the superposition principle. If you have a linear ODE with several inputs like F1 and F2, then you can split this more complicated problem into simpler ones, like we have done here. You solve one ODE with one forcing function, then you solve another ODE with another forcing function, and then you simply add up the solutions. You can only do it with linear systems, because only they obey the superposition principle. Nonlinear systems do not obey that principle. By the way, these equations are called ordinary differential equations because they are only differentiated with respect to one variable. In this case, it's time. If your dependent variable depends on its partial derivatives, in other words, if it's differentiated with two or more variables, let's say partial of E with respect to x, then you're also differentiating this variable with y and also with z, then you would have partial differential equations, or PDEs for short. However, PDEs are not relevant in this course because our system variables are only differentiated with time.